Hey everybody, Chris McClure here. Now we're going to talk about the material in section 1.4 of the textbook. And we're talking about how to go about and get a good sample now that we know that a sample is a subset of the population. Now, our goal is to get more than one member of the population. And of course, the larger the better. That's always going to be the goal, is to have as many individuals from the population as possible. And not only that, have a group of individuals in your sample so that your sample looks like a reflection of the population as a whole. So our goal is to reduce the amount of both statistical and non-statistical errors that we're going to see briefly in this presentation here. Our focus, though, is the idea of getting some sort of random sample, and most likely we're going to be looking to get just simply a simple random sample, and we'll take a look at what that means here real soon. But again, to reiterate, the quality of your sample will directly influence the quality of your analysis. Because after all, you could have, bad data, but perfectly good analysis by, it inputting the data into any number of statistical platforms like JUMP, which is JMP, which I'll demonstrate later in the course, or Excel, or many others, like StatCrunch, which I'll use later in the course with you as well. But if your data is really not very good, then so will the results be. Now we're going to be focusing on two different ways of obtaining data, two different types of doing a statistical study. In other words, one way is the observational study, and the other one is the experiment. Now, the observational study, briefly, is the sort of statistical study in which you are not actively changing anything. You're not tweaking anything. You're not changing any dosages or anything like that. You're just, making an observation, asking a question, measuring some sort of result, but you're not actively modifying anything with the subject that you are studying. Versus an experiment, which there is a treatment or maybe multiple treatments. Or if there is a treatment, just one, maybe there's many different levels of treatment. For example, different dosages of a medicine, for example. Okay? And then, of course, for each level or for each treatment, you will measure the response, both individually and collectively for each treatment group. Okay, so here's an example here. Suppose that we have the Pew Research Center, which does a lot of surveys. A lot of organizations go out there and want to do a independent survey, so they might hire a Pew Research Center to do the survey for them. By the way, if you are looking to become a statistician, this is one of many places that you can apply to go and work. I've seen their advertisements. So the Pew Research Center surveyed so many adults, 2,252 for example, and found that 59% of them go online wirelessly. Now this is a sort of statistical study, but is it an observational study or is it an experiment? Well, in order for it to be an experiment, you need to know what the treatment is. Well, there's no treatment here, so it's an observational study. There's nothing that's being changed or modified or different levels or anything. You're just observing. You're asking the question to each individual. Do you go online using the wireless internet? Yes or no? Here's a different sort of statistical study. Well, way back before I was born, one of the greatest achievements in public health involved the development of the vaccine for polio. By the way, Jonas Salk is a saint in the public health world because he opted to not get a patent for his immunization. And if he did, he would have been fabulously wealthy, but he was a saint, and because he was doing it for the public good. But how did we really know that his treatment was any good? Well, there were actually at least two different iterations of this experiment, but we're looking at the second one here, in which we had 200,745 children were given the vaccine, and 201,229 children were given a placebo. And I'll tell you what a placebo here is in a minute, but it's basically a sugar pill, or in this case, more like a saline injection. And of course, the children probably don't know whether they got the active treatment or they got the placebo. All they know is they got a shot. But the workers, they knew which children got what shot. This is an experiment because some of the subjects got the treatment and the other ones didn't. And we're looking to see, was there a different outcome for those individuals who got the treatment compared to those who didn't. Now, how do we go about choosing the individuals for our sample? Well, the most simple way is just to simply do a simple random sample in which, we have a certain size N. N could be 10, 100, 1,000, 10,000, whatever. Choose your number. And that size for your sample is, you compare your sample against any other sample of that same size. And, for that sample of size, say 1,000 that you had just gotten, every other sample of that same size is just as likely. Just as likely. It's kind of a slippery sort of concept, but it's important statistically. Versus a random sample in which any one individual in your sample is just as likely to have been chosen as any other individual. Then there's the systematic sampling, in which there's some sort of, as you guess it, some sort of rule. For example, you can choose every third individual coming through the gate for a random pat down or screening of his bag. Or, you maybe grab every 10th person as they exit the department store and ask that individual a question. Or you can go into an apartment complex and knock on every third door and ask the head of household a question. Those are all examples of systematic sampling. Another one would be if you want to do a urinalysis for your workforce at your workplace. So what you could do is on a monthly basis, randomly sample a digit. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 digits to choose from. So you can place 10 numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in a hat and randomly select one. And then say, suppose it's a 7. Okay, every employee with an employee number that ends with the digit 7 will present themselves at HR, Human Resources, for random urinalysis. So-called random, it's really systematic. You know, there's no reason to suspect anybody, but it keeps everybody on their toes. And then what you could do is, if you want to make sure you get everybody throughout the calendar year, is as each month goes by, you can randomly sample a digit from the remaining numbers, like 6 or 4 or whatever, and employees with their number ending in that digit will, that next month, get their urinalysis and so forth. Then there's the convenient sampling. Now, this is lazy person sampling, and it's not sampling at all, really. It's basically where you decide that you don't want to put a whole lot of work in getting the individuals for your sample. So you just will do something as simple as ask all the individuals in your workplace or in your class at school, or all the people, all the households on your block in your neighborhood, or everybody at your church congregation. That sort of thing. But the problem with that is those individuals that you are sampling, they together are not a representative sample of the population. I'm pretty sure. Okay. Now, there are going to be times when you're doing a study on something in which, you know, there might be some sort of different overall opinions. But you want to make sure, though, that you get an equal number of individuals from each of the groups. So, for example, you might want to make sure that you have an equal number of men and women. You want to avoid, when you're doing a study regarding sex and marriage and children, for example, you might want to make sure that you get the same number of women as men in your study. So what you do is that you divide your population into women and the men. And then you randomly sample, so many individuals, say 50 women and 50 men. For example, another example of stratified sampling would be if you are doing a study regarding attitudes toward gambling in your community. And you want to make sure that you get an opinion from every neighborhood in your community. Well, then you make sure that you sample so many households from each neighborhood. Okay? Could be 10, could be 20, whatever, but the same number of households. Or it doesn't have to be the same fixed number, but maybe the same ratio or percentage or fraction. If you are concerned about the weight of each neighborhood according to its relative size. Whatever, but the point is that you're making sure that you get some representation from each of the different groups that you really care are being represented in your sample. Now, cluster sampling is different than stratified sampling. Now, let me go back here. Stratified sampling is your sampling from each of the groups. In cluster sampling, your population is broken down into clusters. And then you are going to randomly sample some clusters and then measure every individual in each of the clusters. So, for example, suppose that you want to get a sample regarding people's opinion toward impeachment for the governor. Well, what you could do is you can randomly sample 3 precincts from the state. And each precinct, you can call every household or send a mailer or somehow contact every household or every voter on the voter rolls. Now, that'd be a rather large undertaking, but it's possible. And ask them, hey, should the governor be impeached? Yes or no? And then there's the multi-state sampling. And looking at the textbook, they give really an amazing example of multi-state sampling, in which you have 2 or more stages. If you take a look at example 2 at the bottom of page 26, they give an example of how sampling is done in deciding what the unemployment rate is. So what they do, and I'll just briefly read through this for you, is that, the United States is partitioned into 2,025 different regions called primary sampling units. The primary sampling units are metropolitan areas, large counties, or combinations of smaller counties. These PSUs are geographically connected. The 2,025 primary sampling units are then grouped into 824 different strata. In each of the 824 different strata, one of the PSUs is selected so that the probability of selection is proportional to the size of the population in each PSU. And then each of the 824 selected primary sampling units, census data are used to identify a census enumeration district, with each containing about 300 households. Enumeration districts are then randomly selected. In each of the selected enumeration districts, clusters of about 4 addresses, contiguous whenever possible, are randomly selected. And respondents in the 60,000 selected households are interviewed about the employment status of each household member of age 16 or older. So if you are listening to the news or reading the news paper, for example, or on the internet, and you read that the unemployment rate for the state of Iowa is whatever, 5.2% or whatever, that's an example of how it's done by multiple stages. It could be that there's a systematic sampling at one stage and the simple random sample at a different stage. So here's the list of the different types of or methods of sampling that we've talked about here. Now, let's take a look a little bit more at the various statistical studies, different observational studies and experimental designs. Now, you could be doing a cross-sectional study in which you are taking a look at some phenomenon at one point in time. Like, for example, if you are interested right now today at what is the connection between, say, body composition and television watching habits. What you could do is you can take your sample of people, adults maybe you're interested in young adults, 18 to 25, and in your sample of individuals, you can measure two things. You can measure their body composition by taking maybe the ratio of height to weight, or weight to height, as the measure of body composition. And the other measurement could be the amount of television that they watch per week. And then you would maybe create a scatter plot and to see if there is a relationship between body composition and television watching. But that's just for one point in time. Retrospective is where you go back in time, because maybe it didn't occur to anyone at the time to look forward or do a cross-sectional study, but maybe you can go back and look to see if there's a connection, for example, between, I don't know, for example, number of sexual partners and an individual getting an STD of some kind. I don't know, that might be kind of a weird sort of study to do, but I've seen it done. Or the number of individuals in a car and the number of individuals who died in a car crash, or speed of a vehicle at the time the car crashed versus the amount of damage that was done through the years. Okay, or if you want to see what's the connection between safety and number of hours or number of miles driven through time, you could take a look at the number of collective miles driven by Americans every year since records were kept, and the number of traffic fatalities for each year as well, and take a look at that connection between time, fatalities for traffic, and the number of miles driven. So that's looking back in time for to see if there's a trend. And then there's prospective, where you might want to set up a study from here on out and look at maybe the connection, for example, between the drinking of red wine and the likelihood of getting heart disease, for example. So you can choose 10,000 individuals and on an annual basis visit with each individual and collect data regarding their consumption of red wine, and also measure certain biological characteristics to see if they are showing evidence of heart disease. And do that over, say, I don't know, 50 years, 100 years, or whatever, until everybody has essentially passed. But prospective basically means that you're going from this point forward in collecting data. So you've created the study ahead of time. Now, it's important that, when you design an experiment, that you do as good of a job of randomizing as possible. But there are alternatives to randomizing. But it's the simplest way. You get the most bang for your buck, unless you're really wanting to spend the time to making sure that you've got a wide variety of individuals with all the different sort of characteristics that you want, which is very difficult. The best thing to do is take a good sample from the population on a random basis, a nice simple random sample, and then take that group and randomly select each individual to go into the different groups. Your goal is to make sure that you create your 2 or more groups so that they are similar to the greatest extent possible. Now, when we say replication, the big thing that you need to think here is that make sure that your samples are large enough. Because if you have small samples, then we'll read it right here, that you'll have erratic behavior that is characteristic of small behaviors that will not disguise the true effects of different treatments. So you need large samples, the larger the better, so that individual reactions to treatments or non-treatments will not cover up the overall effect of the treatment or non-treatment. So again, large sample size together with randomness is the good recipe for designing your experiment. You also want to consider blinding of some form. And now blinding refers to not letting the individuals in each group in your experiment know whether they are receiving the treatment or not. So for example, if you're testing the efficacy for a new skin cream to treat eczema, well, maybe you've got your 2 groups. One group will receive a cream without the active ingredient, and the other group will receive the active ingredient. The only difference between the 2 groups treatment or the 2 groups in receiving their skin cream is that the treatment group will receive that active ingredient. But in the blinding, the treatment group, they don't know that they're being treated with that active ingredient. All they know is they're getting some skin cream. And so is the group in the control group. Okay? So, now here's the problem though. If you are receiving this cream, but it doesn't have the active ingredient, now you might still believe though that you are receiving the active ingredient and that this will cure your eczema, in which your body very well might heal itself. That's the so-called placebo effect. Same thing if someone is given a sugar pill but they believe it really is a painkiller. There's a lot of individuals that will experience a decrease in the level of pain. That's the placebo effect. So what we try to do is do a double blinding, in which the individuals in all the groups, they're told that we don't know whether you're receiving the active ingredient or not. You may or may not be. You don't know what you're getting, and neither do the experimenters, the ones who are actually applying that skin cream to your arm that's got the eczema on it. They don't know what you're getting. You don't know what you're getting. So that reduces the placebo effect. The only people who know who's getting what are the individuals behind the curtain, so to speak. The individuals who are not necessarily directly administering, but the managing the experiment, the scientists. And one of the things, though, that we also want to try to reduce is the confounding uh, variables. So, for example, the famous example has to do with men versus women. If you divide your uh, groups into male versus female, and you give the females the active ingredient and the males are the control group, well, whatever sort of overall response that you get from the women, you don't know whether it's truly a response to the treatment itself, the ingredient, the active ingredient, or is it because of the biological differences between males and females. So what you'll want to try to do is make sure that there is an equal number of men and women in each of the groups. So those biological differences are not a confounding variable. Same thing with smokers. You'll want to make sure that you do any sort of study involving smoking for individuals that come from a wide variety of backgrounds, environmental backgrounds. Not just, individuals in the control group who are smokers, but, maybe they have never been exposed to industrial processes versus maybe your control or your experimental group, your treatment group, I should say. Maybe those were individuals from the coast of Louisiana where there are a bunch of chemical plants. So again, that's where randomization comes in. Make sure that you have a good mix of individuals in each of the groups so as to reduce any sort of confounding. Now, a completely randomized experimental design is where you really make sure that, if you have randomly selected, say, a 27-year-old male, who's overweight and smokes in one group, then you have the similar individual in the other group. And you go on down the list. So that you really, take the time and effort to make sure that each group is exactly alike, or as close to alike as possible. That's the completely randomized experimental design. Now, the randomized block design is where you divide the individuals in your statistical study according to certain characteristics versus, like, for example, males versus females, maybe older folks versus younger folks. Maybe you could have 3 different age groups, 18 to 30, 30 to 45, and over 45. Okay, because, people of different ages might respond to your treatment in different ways. Or maybe that's what you want to study. Match pairs design. 2 different ways that you could do this. One would be a before versus after. So maybe you can get all these individuals in your sample, have them submit to a blood pressure test. So measure their blood pressure before you give them their treatment. And then give them their treatment, maybe 2 weeks of administering this daily pill, and then they come back after 2 weeks, and then you measure their blood pressure again. And then you take their systolic after and minus systolic before for each one, and to see if there is a positive average or a negative average or zero. The other sort of match pairs design is essentially the twins design, identical twins. So, hey, guess what? If you are one of an identical twin, you and your twin could probably make a lot of money through the years in participating in experimentals or experiments in which one of you will receive the treatment and the other one will not. And they'll do that across many different pairs of twins. And then they'll look to see overall, the individuals of the twins who did not receive the treatment compared to the group of individuals of the twins who did receive the treatment, see if there's an overall effect. Where the only difference is that one treatment, whether it's a different sort of reading education or given a certain chemical treatment or whatever. Rigorously controlled design. Again, that's where we are using the computer, where the computer knows all the different characteristics of individuals. So if you want to make sure that you have individuals and groups that have certain characteristics, like, for example, high blood pressure, high cholesterol, males, females, whatever characteristics that you're really interested in studying, and making sure that those individuals are selected for each group. So regardless of what approach that you take, you need to make sure that you use randomization to the greatest extent possible, and computers are your friend. Use randomization to select your sample from the population, if at all possible. That may not necessarily be possible because you may have to do with whatever comes your way. But once you get your group of individuals from the population, then randomly assign those subjects to the different groups. Use replication. That basically means get as large of a sample size as possible. And then control the effects of variables by reducing confounding, and use blinding, especially double blinding, which was essentially the gold standard for experimental design. You want to avoid any errors as possible. Now, some are outside of your control. For example, sampling error is going to be the deviation between your sample versus the population. Now, for example, if your population of adults who are residents of Iowa include, I don't know, some sort of characteristic like 78% white or / Caucasian. Well, it could be that your sample of adult Iowans has 82% Caucasian, which isn't too far off, but it is an error. Your goal is to make your sample as close of a reflection of the population as possible. And any deviation in those various characteristics, male versus female, height, weight, Republicans, Democrats, males, females, whatever, between your sample and the population as a whole, that's the sampling error. Again, there's no way that you could possibly control this if you were really doing a random sample. But again, the best thing that you could do is just do a simple random sample and just hope that you don't have the dumb luck of having a sample that is very far off from the actual population. Now, your non-sampling error would be those other sort of mistakes that you do have control over. So, for example, using the wrong way of measuring your data, incorrectly writing down responses, and so forth, asking the wrong questions, biased samples, just the wrong experimental design, whatever. And sampling, you actually design your sample. So if you have a bad design, like you're doing convenient sampling when you should be doing random sampling, well, you're going to get really bad data. That actually, that last one goes with the non-random sampling error. You're just using the wrong method. The non-sampling error is more the technical errors. So that's it for today. We're going to move on in chapter 2 next time, where we'll talk about what to do with your data now that you've got this list of numbers, for example. What do you do with that numbers? How do you turn that data into information? So we will talk about organizing that data and creating these tables and tables. Sorry, I already said that. But these histograms and charts. So we're looking to turn our data into a tool that you can make decisions from. All right, so that's it for next time.